In this video, we're going to be talking about dead stellar objects, that is, all those celestial bodies residual of the last evolutional phases of a star's life, namely planetary nebula, white dwarfs, supernova remnants, neutron stars, pulsars, magnetotars, and black holes. To understand how these celestial bodies are formed, however, we must first briefly describe how stars are formed and how they evolve. All stars are formed within the densest areas of vast molecular clouds present in the interstellar medium, essentially composed of hydrogen with a quantity of helium 23 to 28% and slight traces of heavier chemical elements. These nebulae are also known as HII regions because the hydrogen form which they are composed of is ionized by the ultraviolet radiation emitted by the stars that form inside them. Remember that the notation indicates hydrogen ionized once. If one of these molecular clouds is crossed by the shock wave triggered by the explosion of a supernova, or is compressed by a collision between galaxies, it begins to manifest gravitational instability and then begins to contract due to its own force of gravity, and inside, in the densest areas of the nebula, a protostar begins to form, a celestial body that emits radiation precisely because of the gravitational contraction. At this point in the subsequent stellar evolution depends on the mass of the star at hand. If the mass is less than 8% of the mass of the Sun, the protostar becomes a brown dwarf, a celestial body slightly larger than that of the planet Jupiter, in which the only two sources of energy are the gravitational contraction and the fusion reactions of lithium and deuterium, isotope of hydrogen whose nucleus is composed of a proton and a neutron. The relatively low temperatures of the nucleus, at most a few thousand degrees, prevent the establishment of thermonuclear fusion reactions typical of the most massive stars. Brown dwarfs have typical masses between 13 and 65 times the mass of the planet Jupiter, and in this mass range the fusion deuterium occurs. Under the limit of 13 Jupiter masses, we no longer speak of brown dwarfs, but of gas giant planets. Above 65 Jupiter masses, the fusion of lithium can also occur. Due to their very small masses, brown dwarfs cool down over time and their brightness decreases. Due to their very low brightness, brown dwarfs are not visible to the naked eye. If the mass of the star is larger than 8% of the mass of the Sun, the protostar continues towards the main sequence phase, a phase of stability in which the energy source in stars comes from thermonuclear reactions that melt hydrogen. During this phase, the stars are in a condition of hydrostatic equilibrium, in which the radiation pressure generated by the thermonuclear reactions, which tend to make the stars expand, counterbalances the force of gravity, which tends to cause the star to contract, and in the stellar nuclei temperatures are of the order of tens of millions of degrees. Even in the type of thermonuclear reactions, there's a difference between depending on the mass of a star. In stars with a mass less than 1.5 times the solar mass, the fusion of hydrogen occurs through the proton chain, while in those with mass greater than 1.5 times the solar mass, the carbon cycle prevails. The main sequence phase has a different duration, again due to different masses of the stars. The most massive stars in fact consume hydrogen faster, so they remain in the main sequence for a few tens of millions of years. Examples of this type of star are the Pleiades, stars like the Sun and smaller since they consume hydrogen more slowly, instead remain in main sequence even for billions of years. In the case of our Sun, the main sequence phase is believed to have a total duration of about 10 billion years. Currently our star is more or less in the middle of this phase. But think, the red dwarfs, even smaller than the Sun, could remain in the main sequence for longer than the age of the universe, which is currently about 14 billion years old. It's unbelievable, isn't it? Well, what do you think? Write it down in the comments. To give an idea, think about filling two vehicles with 50 liters of gasoline, a large truck and a small car. Which of the two vehicles will consume gasoline first? Obviously the truck, because being bigger and more massive than a small car, it needs a bigger engine to be able to work. What happens when hydrogen runs out of the core of a star? The star exits the main sequence phase. Since the radiation pressure generated by the combustion of hydrogen fails, the star is no longer in a condition of hydrostatic equilibrium. It will therefore tend to contract. The outermost layers of the star will then press on the innermost ones and on the core, exerting a certain pressure upon them. This increases in pressure on the central regions of the star will increase the core temperature up to values of the order of 100 million degrees, so that the new thermonuclear reactions will be triggered. This time, however, it will no longer be hydrogen to burn, but helium, and this process will produce carbon and some oxygen. The effect is that the star will expand and become a red giant. In the case of the Sun, it's believed that it will become such in about 5 billion years. If the Sun of this very distant future were in the place of our current Sun, its outer gaseous envelopes would become to lick the orbits of Venus, and even the Earth would most likely not fare well. What could happen in your opinion? Write it in the comments below. After the red giant phases, the evolution of stars continues differently depending upon their mass. In the case of less massive stars, therefore also of our Sun, the outermost layers of the red giant will slowly expand into space, a bit like a swelling soap bubble, and form planetary nebula. It is important to point out that planetary nebulae have nothing to do with planets. It seems that this denomination was first proposed around 1780 by William Herschel, to whom these expanding gas bubbles observed through his telescope clearly reminded him of planetary systems in the process of formation. Observed through the telescope, the planetary nebulae appear to be round in shape, and the appearance of some is somewhat reminiscent of a donut or smoke ring. Examples of nebulae are M27, which can be observed with the 20-centimeter telescope in the direction of the constellation of Vulpecula, and M57 in the direction of the constellation of Lyra. And what happens to the rest of the star, or the central part? Well, a white dwarf is formed, a very dense and compact object. Think that a white dwarf is about the same size as our planet, but contains a quantity of matter equal to at most 1.4 times the mass of the Sun. The value of 1.4 solar masses is known as the Chandrasekhar's limit, in honor of the astrophysicist Subrahmanyan Chandrasekhar, who derived it. This value represents the upper limit of the mass of a white dwarf. The densities of them are insane, more or less in the range of 1,830,000 grams per centimeter cubed. In practice, if you take a cube with a side equal to 1 centimeter, it would weigh about 1,830 kilograms, or almost 2 tons. What would happen to you if this cube fell on your foot? Write it down in the comments below. Due to their low luminosity, white dwarfs are not observable through the naked eye, but through Newtonian telescopes with at least 20-centimeter apertures, or at least the brightest ones can be seen. One of the most famous white dwarfs is Sirius B, companion of the more famous star Sirius, in the constellation of Dog Major, just over 8 light-years away from Earth. What happens to the most massive stars instead? Well, they also pass through the red giant phase, but due to their greater masses, the combustion of helium in the nucleus occurs much faster, so when the helium runs out, the radiation pressure triggered by the combustion of the helium and the same violent collapses on itself due to the force of gravity. This causes a sudden increase in temperature in the core and furthers thermonuclear reactions during which the chemical elements heavier than carbon and oxygen are produced. The very rapid increase in temperature causes the outer envelope of the star to expand violently into space in an explosive way, thus producing a supernova explosion and originating a supernova remnant. Some famous examples of supernova remnants are also observable through an amateur telescope. For example, the Crab Nebula M1 in the direction of the constellation of Taurus, about 6,300 light-years away from Earth. The supernova explosion that originated it was observed by the Chinese in the year 1054, who recorded it as a host star. According to the Chinese documents, it reached a peak of magnitude of -6, so to speak 4 times brighter than the planet Venus. Petroglyphs found in Navajo Canyon and White Mesa in Arizona and in Chaco Canyon National Park in New Mexico appear to be representations of the event by the Anasazi Indians. M1 was observed by the French astronomer Charles Messier in 1758 while he was looking for Halley's Comet on its first expected return, another very famous supernova remnant in the spectacular Swanvale complex, much appreciated by astrophotographers. What remains of the nucleus also becomes a very dense and compact object, but not a white dwarf, but a neutron star. With these objects, the matter is degenerate, that is, it's so compressed that electrons and protons combine together to originate neutrons, due to the weak interaction. The range of masses typical of these celestial bodies are between about 1.4 and 3 solar masses, therefore higher than Chandrasekhar's limit, so while the diameter is around 10 kilometers. If you've already been amazed by the density of a white dwarf, the density of a neutron star of 3 solar masses is even more incredible. 1,015 grams per centimeter cubed. In other words, it's almost 800 million times greater than the previous one. It is definitely good that a cube of a neutron star matter does not fall on your head. There are several types of neutron stars, the most important being the following. Pulsars. These are neutron stars that emit 2 beams of radio waves from the poles and rotate very quickly upon themselves, a bit like a lighthouse at the port. The fastest pulsars even spin at 1,000 times on themselves in just 1 second. The first pulsars were discovered by astronomer Jocelyn Bell in 1967. They're not visible to the unaided eye, but through their emission in the radio band, if you have any amateur radio friends, you can ask them to let you listen to the sound of pulsars. Magnetotar. They're similar to pulsars, but are characterized by a very strong magnetic field, from 10 to the 13th to 10 to the 15 Gauss, billions of times more intense than the Earth's magnetic field, which is instead about 1 Gauss. Because of these very intense magnetics, magnetotars also emit soft gamma rays. What if the star has an initial mass greater than 3 solar masses? After the supernova explosion, its core does not become a neutron star, but collapses into a black hole, a celestial body with a gravitational field so immense that not even light can escape. A black hole to our eyes is invisible precisely because it does not emit light. From a relativistic point of view, a black hole is a region of space-time with a very large curvature. If you haven't already done it, drop a line below and let us know what you think.